Chapter 2.3 Momentum. Don't confuse momentum with moment. Moment is force into perpendicular distance from the pivot to the line of action of the force. This is momentum. Momentum is the mass of the object times its velocity. By the end of this section, you should be able to calculate the momentum of an object, explain how momentum is gained or lost. So here is the definition of momentum. These are the units. The unit of momentum is kilogram meters per second in base units or SI units, and this is the unit of mass, this is the unit of velocity. Okay, so the heavier an object is and the faster the object is moving, the greater the momentum. Mass is a scalar quantity, velocity is a vector quantity. I have mentioned earlier that if you multiply a scalar by a vector, the result is a vector. That is what they mention here. And the direction of the velocity is the same as the direction of the momentum. This means its direction is very important and must be kept in mind. The direction will be the same as that of the velocity. That is, the direction of momentum and velocity are the same. Which objects move with greatest momentum? Okay, so you can see here this is a bullet, but it's very light. However, the speed is very high. So I told you, the greater the speed, the greater the mass. You can see it from the equation. Greater the mass, greater the speed, greater the momentum. Okay, so this ball here, shot put, that is very heavy. In this game, you would have seen this in the Olympics also. Those who are doing athletics may be familiar with this. So this is very heavy. So the mass is very high. Okay, maybe it's not moving with very high speed, but because the mass is high, the momentum can be high. Now in this case, the mass is great, the velocity is also great, so it will have a very large momentum. The speed of this is very high, okay, even though the mass is small. And in this case also, he has a certain mass and a certain velocity, but this would be the one having the greatest momentum. Okay, let's go through this example. In an athletics hammer has a mass of 7.26 kilograms, men's competition standard, and can be released at speeds in excess of 25 meters per second. Its momentum at 25 meters per second would be, again, very easy. You can use the equation. You're supposed to find the momentum. The mass is given 7.26 and the velocity is 25 meters per second. So you can find the momentum, 182 kilogram meters per second. A bullet can have a mass of 4.50 grams and can be fired at a speed of 925 meters per second. The momentum of this example bullet would be, so the speed is given, the mass is given. Remember, the mass has to be in kilograms so that your answer will be in kilograms meters per second, and also this unit of this here should be in meters per second. So it's already in meters per second. Then we can convert the grams to kilograms by multiplying by 10 to the power of minus 3, or in other words dividing by 1000. So this will be the answer. Now you can see from these examples, it would be significantly more difficult to stop a well thrown athletics hammer than a bullet, because the momentum of the hammer is very high. So the greater the momentum, the more difficult it is to stop it. For example, a bullet, maybe with a thick piece of wood we can stop it, but we can't stop this motorcyclist with the same sized piece of wood, because this has a much greater momentum. So greater the momentum, the more difficult or the more force is that is required to stop it. It would be significantly more difficult to stop a well thrown athletics hammer than a bullet. So that athletic hammer is also something similar to this, where the athlete he turns around and throws it. Okay, that's also an Olympic game. So what exactly do we mean by more difficult? Okay, then these are the Newton's second law. I have created a video explaining the Newton's laws in detail. It's in a separate video. Anyway, this Newton's second law and the momentum equation, they are very important. I have already shown this, I think, previously also. We know I can show it again very quickly because it's very important. we have the Newton's second law equation, that is F equals ma. Then we also learned the equation acceleration is equal to change in velocity over time. Then over here for acceleration we can write v minus u over t. So this will become mv minus mu over t if you remove the bracket. Now you learn the equation for momentum. Momentum is mass times velocity, and here this is the final momentum because we are using the final velocity here. So this will be that, and this will be the initial momentum because we are using the initial velocity u here. So what we have here is the final momentum minus the initial momentum. Final minus initial is the change. So we can also write this as change in momentum. We can use the Greek letter delta to indicate change in momentum. Now you can see this here is always the resultant force. In F equals ma we can even use the letter sigma to indicate that it is the net or resultant force. So that we have the resultant force is equal to the change in momentum over time. Change in momentum over time is the rate of change of momentum. Okay, so you have to know all these equations in these different forms. And if you go further, if you move the t to this side, then it will be the resultant force times t is equal to the change in momentum, and this is what we call the impulse. We use the capital letter I to say that it is the impulse. Alright, so impulse is the force, the resultant force times the time. Some books use the letter sigma to indicate it is the net or resultant force. Some books don't use that, but still it's the resultant force. Okay, so going back, so that's how they get this. And so here is actually a graph. Now if you plot a graph of momentum over time, okay, so what they are basically doing there is now this one. Okay, so if you plot a graph of momentum versus time, the gradient would be the force. Now again we can rearrange this. Actually change in momentum is equal to F times t. So that means if the force is constant, we can write it like this: y equals mx. What we have on the y-axis is the momentum. So this is actually it's the change in momentum. Now if the initial momentum is 0, then the final momentum and the change in momentum are the same. So this f will be the gradient, and what is on the x-axis is what we have is the time there. So this is what we have. So you see, very easy investigating momentum change. You can investigate the rate of change of momentum in the school lab if you record the movement of the trolley over time as a force makes it move from rest. You can find its velocity each second. Now in this case, the force on the trolley is constant. The force on the trolley, which is the tension in this string, is the same as the weight of these slotted masses and the mass hanger. This hook-like thing that is it is part of the mass hanger. The slotted masses are added to that. So the weight of this whole thing here will be the tension in this string, and we assume the pulley is smooth. Then the tension here and the tension here will be the same. So the force, the resultant force on the trolley is actually the tension in the string. We assume there is no friction here between the wheels and this thing. Then we can see the force is constant. Now what happens with time? Because there is a resultant force on the trolley, there will be an acceleration. That means the speed will increase with time. So you have learned that if there is a resultant force, if the mass is constant, then there will be acceleration. So it starts from rest, so we can say u is 0. Now when there is acceleration, that means the speed will increase. So we know that momentum is mass times velocity, and if the v increases, if m is constant, then the momentum will increase. So in this case, the momentum will increase with time because the speed is increasing with time. So the gradient of the momentum versus time graph is the resultant force, and that is constant. You can see in this also. You can investigate the rate of change of momentum in the school lab, and you can see momentum divided by time, that is the rate of change of momentum, which is in other words the resultant force. So the change in momentum over time is the resultant force. Again, the gradient of this graph is the resultant force. You can find its velocity each second. If you then calculate the momentum each second, you will be able to plot a graph of momentum against time. It should be a straight line, as momentum is equal to force times the resultant force times time. P equals Ft. The gradient of this line will be equal to the accelerating force. And this definition is very important, and that's the end of 2.3 part 1.